The U-boat surfaces in the black waters of the North Atlantic. It's March 17th, 1943. Kapitan Lieutenant Klaus Hartmann scans the horizon through his periscope, confident. His Type 70C submarine has sent 3 Allied merchant ships to the bottom this week alone. He sees nothing. No aircraft, no destroyers. The night belongs to him. What he doesn't know is that 12 miles away, a coastal command liberator is already diving toward his position. The pilot, Flight Lieutenant James Morrison, stares at a glowing screen in his cockpit. Something impossible just months ago. A bright dot pulses on the display, marking the U-boat's exact location with terrifying precision. The new centimetric radar can detect a submarine's conning tower from 15 miles away, even in total darkness, even through clouds. Hartmann's lookouts see nothing until it's too late. The depth charges bracket his boat with surgical accuracy. U-523 goes down with all hands. It's the 41st U-boat lost in May 1943 alone, the highest monthly toll of the entire war. In Berlin, Gross Admiral Karl Dönitz stares at the casualty reports with growing horror. His wolf packs are being slaughtered. The statistics are catastrophic. In the first 4 months of 1943, German U-boats sank 108 Allied ships, but in May alone, the Allies destroyed 41 U-boats while losing only 34 merchant vessels. The kill ratio has reversed overnight. They see us, one U-boat commander radios back to headquarters. Day or night, through fog and storm, they always find us. It's as if they have magic eyes. They do. But the technology making this possible, the cavity magnetron that powers every microwave radar in the Allied arsenal, almost never got built. The British invented it in 1940, but when they brought the revolutionary device to America in September of that year, American military experts declared mass production absolutely impossible. The problem was precision. Each magnetron required handcrafting by skilled technicians. Britain was producing 17 per week, enough to equip a handful of aircraft and ships, but nowhere near enough to turn the tide of war. The Allies needed thousands, tens of thousands. What the military establishment didn't know was that in a cramped workshop in Massachusetts, a grammar school dropout with no engineering degree was about to solve the unsolvable and change warfare forever. September 19th, 1940. The Wardman Park Hotel, Washington, D.C. British physicist Edward Bowen opens a wooden box. Inside, nestled in velvet, sits a copper cylinder the size of a hockey puck. It's a cavity magnetron, and it's about to change the war. Vannevar Bush, head of America's National Defense Research Committee, leans forward. He's seen radar before. The British chain home system helped win the Battle of Britain, detecting German bombers at 70 miles. But those massive coastal towers operated on wavelengths measured in meters, too long to provide detailed images or fit an aircraft. This device is different. It generates microwaves, centimetric wavelengths that can detect a submarine periscope, map terrain through clouds, or guide anti-aircraft guns with pinpoint accuracy. In laboratory tests, it produces 400 watts of microwave power, 10 times more than anything America has built. This is the most valuable cargo ever brought to our shores, Bush declares. But there's a problem, a massive problem. John Randall and Harry Boot, two physicists at the University of Birmingham, invented the cavity magnetron in February 1940. Their design is brilliant but complex. The copper block contains precisely machined resonant cavities arranged around a central cathode. Manufacturing tolerances must be exact, down to thousandths of an inch. The vacuum seal must be perfect. The magnetic field must be precisely aligned. In Britain, skilled craftsmen at GEC and BTH are hand-building them one at a time. The production rate by late 1940, 17 magnetrons per week. Each one takes 40 hours of meticulous labor. Expert machinists file, measure, and test each component. The rejection rate is nearly 30%. MIT's newly formed radiation laboratory gathers America's top physicists to improve the design. They produce working prototypes. The Navy orders hundreds for shipboard radar. The Army Air Forces demands thousands for bombing and navigation systems. Coastal Command needs them to hunt U-boats. Anti-aircraft batteries require them for fire control. The total requirement, tens of thousands of magnetrons, and they need them now. In October 1941, Raytheon wins a contract to mass produce the devices. The company's engineers study the British blueprints and deliver their verdict. These cannot be manufactured at scale with current methods. Each unit requires hand-fitting by master craftsmen. We estimate production capacity of perhaps 100 units per month if we triple our workforce and train them for a year. The room erupts in frustration. Navy procurement officers slam tables. Army generals demand alternatives. MIT scientists insist the precision is non-negotiable. Any deviation will cause the magnetron to fail. Then we lose the war, an admiral states flatly. The U-boats are sinking 700,000 tons of shipping per month. Britain will starve by spring. Without submarine hunting radar, the Atlantic is a graveyard. The math is brutal. At 17 magnetrons per week, it would take 9 years to equip the Allied forces adequately. The Allies don't have 9 months. Meeting after meeting produces the same conclusion. Impossible. The tolerances are too tight. The vacuum seals too difficult. The assembly too complex. Military planners begin discussing rationing. Which aircraft get radar? Which ships? Which gun batteries? Every choice means Allied sailors and airmen will die. At Raytheon's headquarters in Waltham, Massachusetts, company president Lawrence Marshall convenes his senior staff. Gentlemen, the Navy is asking for 2,600 magnetrons per day within 1 year. Our current production rate is 0. The experts say it cannot be done. He looks around the table. I have one more man I want to hear from. The door opens. A thin man in shirt sleeves enters. No jacket, no tie. Percy Spencer is 47 years old. He never finished grammar school. And he's about to prove every expert wrong. Percy LeBaron Spencer was born July 19, 1894, in Howland, Maine. His father died when he was 18 months old. His mother abandoned him to his aunt and uncle. When Percy was 7, his uncle died too. Orphaned twice by age 7, Spencer went to work at age 12 in a weaving mill to support himself. His formal education ended in the 6th grade. He never attended high school. He never took a college course. He never earned an engineering degree. But Percy Spencer possessed something no university could teach, an insatiable curiosity about how things worked. At 14, he heard about a new paper mill being built nearby, and that it would have electricity. He'd never seen electric lights. He walked to the construction site and talked his way into a job installing the electrical system, despite having 0 experience. He learned by watching, asking questions, and experimenting. Within months, he'd taught himself practical electrical engineering. At 18, Spencer joined the U.S. Navy. During World War I, he became a radio operator, teaching himself wireless technology at night while other sailors slept. He studied calculus from textbooks. He took apart radio equipment and rebuilt it, understanding every component. After the war, he joined Raytheon in 1925 as a tube designer. He had no credentials, no references, no degrees, but he could solve problems nobody else could touch. By 1941, Spencer holds the title of chief engineer, but the executives barely understand what he does. He works at odd hours, disappears into his workshop for days, emerges with solutions that work, but that trained engineers can't explain. He holds over 60 patents. The Navy has already awarded him its Distinguished Public Service Award for radar innovations. When Lawrence Marshall presents the magnetron challenge, Spencer listens silently to the engineer's explanations of why mass production is impossible, the tolerances, the hand-fitting, the skilled labor shortage. Then he asks a question that stops the room cold. Who says we have to build them the way the British do? An MIT scientist bristles. Mr. Spencer, with all due respect, you're not a trained physicist. The cavity dimensions must be precise to within. I know the specs, Spencer interrupts. I'm asking why we can't use mass production techniques. We make millions of radio tubes. Why can't we stamp, punch, and braze magnetrons on an assembly line? The room explodes. That's not possible. The precision required exceeds stamping tolerances. The vacuum seals can't be brazed. They must be individually fitted. The resonant cavities must be machined to exact specifications. This isn't a radio tube, the physicist insists. This is a precision scientific instrument. No, Spencer says quietly. It's a weapon, and we need 10,000 of them by Christmas. Marshall makes a decision that will alter the war's trajectory. Spencer, you have 60 days and whatever resources you need. Show us it can be done. Every credentialed expert in the room believes Spencer is about to fail spectacularly. They have no idea what's coming. Spencer vanishes into Building 2 at Raytheon's Waltham plant. He takes with him 4 technicians, 2 machinists, and a British magnetron to dissect. For 3 weeks, nobody sees him. Engineers knock on his door with questions. He doesn't answer. Marshall asks for progress reports. Spencer sends back, "Still thinking." Inside the workshop, Spencer has covered a wall with drawings. Not elegant blueprints, rough sketches showing assembly sequences, tool designs, fixture concepts. He's approaching the magnetron not as a scientific instrument to be perfected, but as a product to be manufactured. The British method starts with a solid copper block. Skilled machinists drill the resonant cavities using precise measurements. Each cavity is individually inspected, adjusted, and hand-fitted. It works, but it's slow and requires master craftsmen. Spencer's insight is radical. Instead of machining cavities into solid copper, what if you stamp them? He designs a punch press system that stamps 8 identical cavity segments from sheet copper in one operation. The segments are then brazed together around a central cathode assembly. The entire core can be assembled by semi-skilled workers using fixtures that guarantee alignment. When he emerges on October 15, 1941, Spencer brings 3 working prototypes. These were made by workers with 2 weeks of training, he announces. Total assembly time, 45 minutes per unit. The MIT liaison examines the magnetrons with visible skepticism. These cannot possibly work. The cavity geometry, Spencer plugs one into a test rig. The oscilloscope trace shows clean microwave output, 400 watts, exactly matching the handcrafted British version. The physicist is stunned into silence. But the military procurement officer shakes his head. "Mr. Spencer, your design is impressive, but even if these work, which I'm not convinced they will in field conditions, you're proposing using semi-skilled labor for precision electronics assembly. The military cannot accept that risk. These devices cost $1,500 each and require expert calibration." "They cost $1,500 because we make them one at a time," Spencer counters. "In production, my method will reduce cost to $200 per unit." "That is absolutely illegal under procurement regulations," the officer snaps. "You cannot compromise military specifications for cost savings. If these magnetrons fail in combat, sailors die. Your approach is reckless and dangerous." The room goes quiet. The military representative is right. Regulations explicitly forbid design changes that sacrifice quality for efficiency. Marshall speaks carefully. Commander, what if we conduct field trials? Give us 3 months to prove they perform identically to the British versions. That is not acceptable, the officer replies. We need production units now, not experimental prototypes. Raytheon will manufacture magnetrons to British specifications using British methods, or we will find another contractor. Spencer's revolutionary design, the one that could arm every Allied aircraft and ship with microwave radar, is about to be killed by bureaucracy. Then the door opens. A Navy captain enters, reading a telegram. His face is grim. Gentlemen, Pearl Harbor has been attacked. We are at war. Everything just changed. December 8th, 1941. The Pentagon is chaos. Reports flood in. The Pacific Fleet is burning. The Philippines are under attack. Wake Island is besieged. America has been thrust into a two-ocean war it's not prepared to fight. In a conference room, Navy procurement officers are reevaluating every weapons program. Captain John Sides, liaison to the MIT Radiation Laboratory, presents the magnetron crisis. Gentlemen, we need microwave radar everywhere, on every destroyer hunting U-boats, every bomber navigating through weather, every anti-aircraft battery defending our cities. Current production capacity, 70 units per month. Requirement, 30,000 units in the next 18 months. An admiral does the math. That's impossible. Not according to Raytheon, Sides says. Percy Spencer has designed a mass production system, but it violates military procurement specifications. The prototypes work, but they're not built to British standards. The room erupts again. Senior officers demand adherence to proven methods. MIT scientists insist any design changes must undergo months of testing. Procurement experts cite regulations requiring component traceability and master craftsman certification. One general slams his hand on the table. We're losing ships every day because we're blind in the Atlantic. This Spencer character, what are his credentials? Sides opens a folder. 6th grade education, self-taught, no engineering degree, but he holds 68 patents and solved the proximity fuse metallurgy problem last year that Bell Labs couldn't crack. So we're going to bet the war on a grammar school dropout? The general's voice drips with contempt. Gentlemen, this is not how the military conducts business. We need proven engineers with recognized qualifications, not some tinker. Marshall stands. General, I've known Percy Spencer for 16 years. He's the most brilliant engineer I've ever met. Degree or no degree. His methods work. His prototypes work. Give him a chance. A chance? The general's face reddens. Do you understand what's at stake? If these cut-rate magnetrons fail in combat, American boys die. If they burn out at sea, ships lose radar at the worst possible moment. If we don't build them at all, Marshall interrupts, we lose the war. The room goes silent. Captain Sides speaks quietly. I've seen the British reports from the Battle of Britain. Radar won that fight. The Germans had superior numbers, but they were blind. We saw them coming. Now the U-boats are winning the Atlantic because they surface at night, and we can't see them either. This new centimetric radar changes everything, but only if we have thousands of units. An MIT physicist adds reluctantly, Spencer's design is unorthodox. It abandons precision machining for stamped components and fixture-based assembly. Every instinct tells me it shouldn't work, but it does. I tested his prototypes myself. They perform identically to handcrafted British units. The procurement officer isn't convinced. Performance in laboratory conditions means nothing. What about durability, vibration resistance, temperature extremes? These devices will operate on ships in North Atlantic storms, in bombers at 25,000 feet in sub-zero cold. They must be absolutely reliable. Then let us prove it, Marshall says. Give Spencer 3 months. If his assembly line magnetrons fail any field test, we'll revert to British methods. But if they work, 3 months? The Admiral shakes his head. We don't have 3 months. We need radar in the fleet now. The argument rages for 2 hours. Careers are threatened. Voices rise. The military establishment demands adherence to established procedures. Marshall and sides insist innovation is essential. Finally, Admiral Harold Bowen, a former engineer himself, stands. Gentlemen, we're at war. That means we take calculated risks. Captain Sides, you will personally supervise Spencer's production line. If quality drops even 1% below British standards, we shut it down. But if this man can deliver 2,600 magnetrons per day, he pauses. Then we give every submarine hunter, every bomber, every anti-aircraft battery the eyes they need to win. He looks directly at the skeptical general. War is won by engineers as much as soldiers. Sometimes by engineers the establishment doesn't recognize. On January 2, 1942, Spencer receives authorization to build the first mass production magnetron assembly line in history. He has 4 months to make it work. If you're enjoying this story of how one self-taught engineer changed the course of World War II, make sure to hit that subscribe button. We bring you incredible true stories of innovation and courage every week. Now let's see if Spencer's gamble pays off. February 16, 1942. Building 2 at Raytheon's Waltham plant has been transformed. What was once a radio tube factory is now something unprecedented, an assembly line for precision electronics. Spencer has designed the entire production system from scratch. 21 workstations, each performing a single operation. Stamp the copper segments at Station 1. Braze them at Station 2. Insert the cathode assembly at Station 3. Each worker has a fixture that guarantees precise alignment. No measuring, no adjustment, no expert judgment required. The first unit rolls off the line at 6:47 a.m. Spencer plugs it into the test rig himself. The oscilloscope trace wavers, stabilizes, 410 watts of microwave power. Perfect. By the end of the first week, production reaches 12 units per day. By the end of February, 80 per day. By March, 180 per day. By April, 600. The statistics are staggering. British production using traditional methods, 17 magnetrons per week with a 30% rejection rate. Spencer's assembly line, 600 per day with a 7% rejection rate. His semi-skilled workers, with 2 weeks of training, are outproducing British master craftsmen with years of experience by a factor of 150. The cost has dropped from $1,500 per unit to $185. Production time, from 40 hours to 47 minutes. But the skeptics aren't convinced. MIT scientists demand field testing. The Navy requires operational validation. These assembly line magnetrons must prove themselves in combat conditions, or Spencer's revolution dies. May 1942. HMS Sterling tests the first radar unit powered by Spencer's magnetrons in North Atlantic convoy duty. The results are extraordinary. Detection range, 15 miles for surfaced U-boats, 8 miles for periscopes. The radar operates flawlessly through storms. Temperature swings from 10 degrees to plus 140 degrees and constant vibration. The Raytheon units perform identically to British-built magnetrons. The Sterling's radar officer reports. Possibly better. We've had 0 failures in 30 days of continuous operation. But the real test comes in combat. July 24, 1943. Lieutenant Joe D. Fentress pilots a U.S. Navy PV-1 Ventura over the Bay of Biscay. His ASV radar, powered by Spencer's magnetrons, suddenly paints a bright contact at 12 miles. He descends through clouds. At 800 feet, his crew spots the U-boat diving desperately. Fentress releases depth charges. U-558 goes down with all hands. We never would have found him without the radar, Fentress reports. The visibility was less than 2 miles. He would have escaped. That magnetron just saved a convoy. The same story repeats across every theater. RAF Coastal Command aircraft, equipped with ASV Mark III radar using American-built magnetrons, sink 17 U-boats in August 1943 alone. Before microwave radar, a submarine sighting occurred once every 30 flight hours. With it, every 4 flight hours. The statistics tell the story. January-April 1943, U-boats sink 108 Allied ships, lose 56 submarines. May-August 1943, U-boats sink 61 Allied ships, lose 123 submarines. The kill ratio has reversed catastrophically for Germany. On August 12, 1943, Gross Admiral Dönitz examines a captured Allied radar set. The magnetron is stamped Raytheon Manufacturing Company, Waltham, Mass. He turns to his technical staff. How many of these do they have? An engineer consults intelligence reports. Thousands, Herr Gross Admiral. They're producing them at industrial scale. Dönitz realizes with cold horror that Germany has lost the technological race. Then we've lost the Atlantic. German U-boat commander Rolf Mutzelberg writes in his diary on September 4th, 1943, "They see us always. Day, night, storm, fog. It makes no difference. Their aircraft appear from nowhere. How can you fight an enemy who has eyes everywhere?" By December 1943, Spencer's production line at Raytheon is producing 2,600 magnetrons per day. The company has become the primary supplier of radar components for the entire Allied war effort. Raytheon magnetrons account for 80% of all units produced during the war, more than 100,000 devices in total. The impact extends far beyond submarine warfare. November 15, 1943. B-17 pilot Captain Robert Morgan flies through solid overcast over Germany. His H-2X bombing radar, powered by Spencer's magnetrons, shows the target city below through 10,000 feet of clouds. His bombardier releases on radar aim point. Bombs strike within 200 yards of the target. Impossible accuracy for blind bombing before microwave radar. June 23, 1944. London is under attack by V-1 buzz bombs, Hitler's first cruise missiles. British anti-aircraft batteries equipped with SCR-584 radar achieve unprecedented accuracy. Of 104 V-1s detected over the English Channel on June 28th, Allied guns destroy 97. Only 7 reach London. The SCR-584 gun-laying radar, powered by Spencer's magnetrons, achieves accuracy of 25 yards in range and 0.06 degrees in bearing. Before microwave radar, anti-aircraft guns required 2,500 rounds to down one aircraft. With SCR-584, 100 rounds per kill. Allied bomber navigator Lieutenant Robert Shaw writes home in January 1944. "The new radar is like having God's own map. We can see cities, coastlines, even rivers through solid clouds at night. We know exactly where we are, always. The Germans are shooting blind, while we have perfect vision." By June 6, 1944, D-Day, the Allied invasion fleet carries more than 10,000 radar sets, most powered by Spencer's magnetrons. They navigate through fog and darkness with precision. They detect German E-boats before they can attack. They coordinate the largest amphibious landing in history with minimal confusion despite terrible weather. General Dwight Eisenhower later writes, "Radar was as important to D-Day's success as any weapon we possessed. It gave us eyes in the darkness and through the storm. None of it would have been possible without the mass production breakthrough of a self-taught engineer who never finished 6th grade." The impact of Spencer's innovation extends far beyond World War II. The technology he helped perfect is still protecting us today. But first, let's see what happened to the man himself. September 2nd, 1945. Japan surrenders. World War II is over. The final statistics are staggering. Raytheon produced over 100,000 magnetrons under Spencer's mass production system. By 1945, Production had reached 2,600 units per day. Exactly what the Navy demanded is impossible. Percy Spencer receives the Navy's Distinguished Public Service Award, the highest civilian honor the service can bestow. The citation reads, "For extraordinary contributions to the development of radar technology essential to Allied victory." At the ceremony, Admiral Harold Bowen tells Spencer privately, "You saved more lives than any admiral or general. Every sailor who came home from the Atlantic, every bomber crew that navigated through the night, every city protected from buzz bombs, they owe their lives to what you built." Spencer is characteristically modest. "I just figured out how to make them faster." But the impact is profound. Historians later estimate that Spencer's magnetron production breakthrough shortened the Battle of the Atlantic by at least 12 months. At the casualty rates of 1942-43, that represents approximately 25,000 Allied sailors and merchant mariners who survived because of earlier radar deployment. U-boat veteran Werner Hirschman, interviewed in 1985, remembers the turning point. "In early 1943, we were winning. By summer, we were hunted animals. They found us every time we surfaced. We called it Schwarz's Mai, Black May. 41 boats lost in 1 month. We knew then we'd lost the war." Spencer returns to Raytheon after the war, continuing his work in relative obscurity. He never seeks publicity. He never writes memoirs. He holds more than 150 patents by the end of his career, many still classified decades later. In 1945, while testing magnetrons, Spencer notices something odd. A chocolate bar in his pocket has melted. Instead of dismissing it, he investigates. Within months, he invents the microwave oven, the same magnetron technology that won the war, now cooking food. The first Radarange weighs 750 pounds and costs $5,000. By 1967, Raytheon introduces the first countertop microwave for $495. Today, more than 90% of American homes own a microwave oven. Everyone traces its lineage back to Percy Spencer's wartime innovation, but Spencer remains humble to the end. He retires in 1964 as senior vice president of Raytheon. He refuses interviews. He declines to write his autobiography. When honors pile up, induction into the National Inventors Hall of Fame, buildings named in his honor, he accepts them with quiet grace and changes the subject. Percy Spencer dies on September 8, 1970, at age 76. The man with a sixth-grade education had revolutionized warfare, helped win World War II, and invented one of the most ubiquitous appliances in modern life. Every microwave radar system flying today, in commercial aircraft, weather satellites, missile defense systems, and even the speed guns police use, descends from Spencer's wartime breakthrough. The U.S. military still uses magnetron-based radar systems in applications where his original principles remain unmatched. At Spencer's funeral, a former Raytheon engineer says it best, "The experts said it couldn't be done. Percy never listened to experts. He just solved the problem." That chocolate bar didn't melt by accident. It melted because Percy Spencer refused to accept that anything was impossible, and because he understood that sometimes the most important innovations come from asking the simplest question: why not?